Good morning, good afternoon, and good evening. Welcome to today's John M. Campbell & Company webcast. Thank you for joining us. My name is Haley Thomas, and I'll be your moderator today. Today's presentation is entitled, A Key to Unlocking Pipeline Stress in Offshore Pipeline Construction. I would like to introduce you to Mr. David Hairston. David is an instructor and consultant for John M. Campbell & Company. He has over 38 years' experience in oil and gas pipeline systems, including project experience in both onshore and offshore pipeline transportation and process facilities, as well as in offshore structures, training, and construction operations. David, the floor is now yours.
Thank you very much, Haley. Good morning and good afternoon and good evening to all of you out there around the world. Thank you for joining us. I'm very happy to be here today to talk to you about a subject with which I've been involved for many years, both in the design and installation of offshore pipelines. One of the things that I would like to discuss today is one of the keys to understanding the pipelay stresses that you incur during the installation of pipelines offshore. And that key is geometry. First, we'd like to talk about the overall geometry to help define the terms that will help us understand how geometry is such an important part of understanding the stresses. Now, the key components of an offshore lay system, in this case we're showing an S-lay configuration that would be typical for very many pipeline operations around the world. This system has been in service, been used for at least my entire career, which is over 40 years now. And the major components that we'd be dealing with would be the actual lay barge itself. This is a surface vessel on which you'd be assembling the pipe. The second major component would be a component called a stinger, pontoon, or truss, depending on what company you're working with and the types of equipment that you're actually dealing with. And this piece of equipment shown here is a transitional piece that takes the pipe from the surface on the barge where it's assembled and transitions from that into the ocean. The third major component of this would be the pipeline itself, shown here as a long golden line in the flattened S configuration, which is the key to us understanding the geometry of the pipeline systems in an S-lay configuration. Now, a couple of other items that are very important for the geometry, understanding the geometry, would be the water depth itself, which is, I think, pretty obvious. And the second is that there's three major components to the geometry itself. The first being the overbend region. The overbend being that portion from above water where you're assembling the pipe over the stinger or truss and down into the water until you reach a point of inflection. Now, the point of inflection, of course, is where the curvature changes from being curved downward in this case to being curved upward in the next component of the geometry, which is the sag bend itself. Now, this point of inflection is an important point to consider and one of the keys to understanding the overall geometry, and from the geometry understanding the stresses that are associated with a lay barge. Now, let's move over and take a look at a picture of a lay barge, and some of these components can be pointed out in a little more detail. This is a semi-submersible lay barge. Some of you that have worked in the business will recognize it as one of the older pieces of equipment, but quite capable. This vessel is one of the larger lay barges. It's a moored system in that it works off of anchors itself. And if you look closely at your screen, you can actually see the anchor lines itself. The pipe is brought on board. You can see some of the pipe being brought to the job site from this supply boat. And you can see the cranes are the way that the pipe is being brought up and stored on the pipe for various operations. The pipe is then put into an assembly line area. In this case, it's down the center line of the vessel, where it is welded, the coating is finished, and inspected. At that point, it begins its transition from the assembly area on the barge into the water, in this case, over a truss-type device that makes that transition. Now, again, if you look closely, you can see down in the water that this piece of equipment does transition from being in air to underwater, and you can also see located there supports that provide support to the pipe, and these are roller type assemblies that help in the transition. Okay, so a lay barge. This is the lay barge where the assembly is done. This is the stinger truss configuration to help the transition, and of course then we have the object of all this activity, the construction of the pipeline itself. Okay. Now, let's move on and talk a little bit about the structural mechanics that go along with this. Okay. Now, some of the key drivers that are involved with understanding the stresses and the geometry of the pipeline would be things as you would expect, like pipeline diameter, the pipeline wall thickness, and its grade. And the grade we refer to is what's the SMYS, or specified minimum yield strength, and would be the numbers you'd associate with API 5L grade materials, the most common pipeline materials. I'm talking about steel materials. The actual weight submerged in water. This is an important consideration because as we take the pipe from its in-air condition and transition it into the water, it's going to displace a volume of water equal to its coated diameter, and that will dramatically reduce its weight to what's called the weight submerged or submerged weight. Another key driver is, of course, the water depth. The greater the water depth, the longer this span is going to be to takes the pipe to transition from the barge to the seabed. It's also going to have impacts on how much weight do we need on bottom stability and other issues. Now, a key factor during construction is how much tension do I apply to this pipe. Now, as we mentioned in the lay barge picture on the previous one, that vessel was a moored vessel. It used anchor lines and cables as a way to hold it in position. There's other types of vessels that will use large thrusters, these being called dynamically positioned vessels, and there's some large lay vessels that are actually dynamically positioned. Now, why is this important? It's important because I need to react or have an ability to hold this vessel in place while I do the pipeline assembly and apply tension to the pipe, usually some distance down once I've gotten part of the welding completed, and apply tension to this pipe. The tension will then have a major impact on controlling what this curvatures and the configuration of this pipe will be. It'll have an important impact in terms of what the radiuses will be down in here in the sag bend area. It'll also have a major impact of locating where the point of inflection is along the pipe where I transition from overbend to sag bend. Now, on the barge itself and the stinger, the barge and stinger, I can also have control stresses, or in this case, the radius of the pipe, by setting the elevations of pipe support rollers on the barge and on the truss itself. You notice on the picture I showed, we pointed out one of the rollers on the truss assembly. Now, what are the key stresses? Well, in terms of pipe lay operations, you predominantly worry about two types of stress. One is axial, and this is generated by the tension that is applied to the pipe on the barge, again, to control the overall configuration. This will lead to some elongation of the pipe, as you would expect. It's going to stretch somewhat. But given the lengths of these spans and the movement of the vessel and stuff, this is a non-problem in terms of dealing with the overall elongation. What's more important is dealing with the bending of the pipe itself, because when I bend the pipe, because of generated moments, I'm going to get curvature. Okay, curvature here in the overbend, and then curvature again in the sag bend. Now, what's important about bending moments is the fact that when the pipe bends, it will create a radius of curvature. At each given point, this radius of curvature will be changing as I span from the transition into the water through the point of inflection and ultimately down to the seabed. And that's directly related, the radius of curvature is directly related to the bending stress. Okay, now let's talk about the stresses for a minute in a little more detail. This axial stress is quite simple. It's basically the tension that's applied to the pipe, okay, and then divided by the metal area where this force or tension is distributed around the circumference of the pipe. It'll be uniform around the circumference of the pipe and usually represents a relatively small stress percentage of the overall allowable stress in the pipe. Let's run an example to see how big these numbers can be. For example, we have a 36-inch diameter pipe, a 0.750-inch wall thickness pipe. We're going to assume that the applied tension is 40,000 pounds, a high number, but certainly not as large as it can be. The metal area for this pipe is about 83 inches squared. Do the mathematics in the equation, and you'll find that the actual stress is about 4,800 psi. If I'm looking at a X60 grade pipe, we're talking about about a little under 8% of the overall yield strength of the pipe is being utilized to accommodate the actual stresses in the pipeline. Now, the diameter of the pipe can have a fairly significant impact. For example, if this was a 12-inch pipe, 12.75-inch OD, and instead of a 3/4 inch, it was 0.375-inch diameter pipe, cut the tension in half, 200,000 pounds, instead of 400,000 pounds, you'd find this stress would go up pretty dramatically because of the dramatically reduced metal area. Instead of being about 5,000 psi, it would be over 17,000 psi. So this level of axial stress is very dependent, of course, on the tension as well as the size of the pipe and the overall metal area. Okay, now let's talk about the other major component, which is bending stress. Okay, as long as we're in the elastic range, a formulation that gives you an accurate calculation of the stress due to bending, in this case generated by the moments, is the elasticity of the material itself, E. Of course, this is very much a material property. For steel, it's 30 million psi, times the radius of the pipe, R. Okay, knowing the outside diameter of the pipe, we can easily calculate the radius. And then the actual radius of curvature along the actual configuration of the pipe itself. All right. Now, we're going to make some assumptions here in our example. Again, we're going to use a 36-inch diameter pipe. It's going to have a 0.750 wall thickness. We're going to assume a radius of about 1,000 feet. Keeping all the units consistent in pounds and inches, we can do the mathematics, and we come up with the answer that the stress due to bending is about 45,000 psi. Now, again, if this was an API 5L X60 or 60,000 psi yield strength material, specified minimum yield strength, that means in bending we're going to utilize about 75% of the overall strength characteristics available to us in the elastic range for that pipe. So these stresses can get quite large. This is also a realistic calculation of the types of numbers that you would see for the maximum stresses of a large diameter pipe and installation and water depths, for example, that would be 600 to 1,000 foot water depths. It would be very common for the stresses to be at and above the 75% of specified minimum yield strength. Okay. Now, again, as another example, we'll look again at our 12-inch pipe. So instead of 36, it's 12.75. Instead of a 3/4 inch wall, it's 0.375 inch wall thickness. We'll use the same radius. Plugging in the new numbers, instead of 45,000 psi, we now get about 16,000 psi. So the diameter of the pipe, as you would expect from the equation, has a pretty dramatic impact on the bending stresses of the pipe itself. Okay. Now, let's go back to our geometry and break it down piece by piece. First, let's talk about the overbend area, or the portion from the barge, over the truss, over the stinger, from the barge, over the stinger, and down to the point of inflection. All right. Now, in this region, we can control the stresses with two things. One, the tension, obviously, in the pipe, but more importantly, the radius that we set the support shoes on the barge and on the stinger. We can dictate what this radius is. Since we've dictated the radius of curvature, we know the pipe, we know the material properties, we then can control the bending stresses in the pipe. Okay. As you get into the water, it's going to be the tension and the actual weight of the pipe, hence it's what we call buoyancy or submerged weight of the pipe. It'll be negative, so it'll actually try to sink on you until you get down to the point of inflection. Now, this is a very important point that we need to talk about for a couple minutes. As the pipe comes off of this truss at the predetermined radius, that radius is going to get larger and larger and larger as it approaches the point of inflection until the point that the radius is about infinity. If at these very, very large radiuses, that means the bending stresses are very, very small, and for all practical purposes, they're zero at the point of inflection for bending. Now, on the barge, we have the same situation. On the barge, where it's level and flat while we begin our welding operations until we get to the tensioners, and ultimately we start the bending over the back of the barge and the stinger, we start out with a zero bending stress condition for the pipe there as well. So for the overbend, we go from very low to zero bending stresses. Could be relatively high, but controlled bending stresses over the stinger or truss. and back again to near zero bending stresses as we go through the point of inflection. The geometry will be such that there will be a dimensional drop or increase in water depth of the pipe that we can characterize as D overbend, that represents the change in water depth of the pipe as it reaches this point of inflection. Okay. Reemphasizing here, the overbend is controlled by the stinger supports, the radius we set those at, as well as the submerged weight or negative buoyancy of the pipe itself. Okay, so that's the overbend. So that's the first segment of geometry that we consider. The second section that we'll look at is the sag bend. Now, things are a lot more interesting and less subject to our control because they're now in the water and no longer on a vessel where we can actually set the radius of shoes, etc. Point of inflection is the starting point for the sag bend. Again, the radius of curvature here is quite large, approaching infinity. Therefore, our bending stresses are going to be quite small, approaching zero. At the other end of the sag bend, where the pipe is now laying on the seabed, again, the radius of curvature is going to be very large, approaching infinity, and the bending stresses are going to be very large. But to make that geometric transition from the point of inflection to the touchdown point, we're going to have to bend the pipe as well as change its angles. Therefore, we're going to have bending moments and bending stresses in the pipe. At a point in the sag bend, usually quite near the seabed, you're going to reach your minimum radius of curvature, or sag bend, and since that's your minimum radius of curvature, that will be your maximum bending stresses. Again, because of the geometry of it such, up to the point of inflection, there will be a lifting or elevation change at the end of the pipe, the sag bend. And then if we look at the point of inflection, this angle at the point of inflection and the elevations need to be consistent with matching what's happening in the sag bend. All right. Now, some summary points. Maximum bending stresses in the sag bend will be at the point where we have the minimum radius of curvature. Control those stresses means we need to control the radius of curvature, and we do that by controlling the pipe weight and the barge tension. Now, to think about this configuration, you need to visualize it as like a catenary. That's a very apt description of the geometry of this curve. Now, it won't be a true catenary because the pipe will have some bending stiffness to it, which will modify the actual geometry, but its basic shape is very much like that you'd see for any kind of wire rope or chain that's suspended and in a catenary. And as with any catenary, water depth is going to be a key variable. The size or strength of the material is going to be a key variable, and its weight is going to be a key variable. So to control the configuration in the sag bend, I need to control pipe weight, I need to control pipe tension for a given pipe size configuration. Okay. So now we've talked about the overbend, coming off the barge at the surface into the water, down to the point of inflection, and now from the point of inflection down to the touchdown point, which is the sag bend. Okay, park this. Overall, the geometry then must match at the point of inflection. So if I look at the elevation change from as the pipe enters the water down to the point of inflection in the overbend, D overbend, plus the change in elevation from the point of inflection down to touchdown point, or D sag bend, those two added together should be equal to and must be equal to the water depth. In addition, the angle at the point of inflection has to be equal at the end of the overbend and at the start of the sag bend. Combined, if you look at the water depths, pipe size, pipe weight, and tension combinations, the radiuses that you used at the surface of the configuration over the stinger and the truss, then you'll end up with a unique combination of the overbend and sag bend geometry, and hence an overall a unique combination of stress distribution along the length of the pipeline. So what have we learned from this? Well, first of all, bending stresses, excuse me, bending stresses during installation can be some of the largest stresses that you'll actually see in the pipeline during that period of installation. It's important to remember that installation is a very short period during the overall operational life of a pipeline. And often the stresses that the pipeline is subjected to during installation will be significantly larger than any stresses it will experience during its operational life. This has a direct impact on the design of the pipeline, selecting of wall thicknesses and weight selection, etc. That the bending stresses are definitely a function of pipe diameter and the radius of curvature, and the radius of curvature is a function of pipe weight and tension. If you want to control your bending stresses, you control radius of curvature. And I do that with pipe weight and pipe tension. Now, from a practical standpoint, when you look at the installation of it you obviously will have to select or pick a lay barge to do your work. And its capabilities, particularly in the area of applied tension, is a key variable that needs to be brought into your overall planning, design, and of course it'll have impact on your cost of your pipeline system during the construction. We can make some generalizations about looking from the geometry based on the very quick evaluation that we've done here this morning. If I increase water depth, I will increase stresses. I think that makes sense to anyone. I'm going to have a longer span from the surface to get to the touchdown point on the seabed. I'll have longer suspended spans from the truss or stinger to get to the seabed. I'll usually have higher stresses as well. All right. If I increase the weight of the pipe, I will increase those stresses, particularly the bending stresses. And again, I think this is fairly obvious. If you think about a catenary where I take a lightweight rope and pick it up, I can flatten it out with very quickly. I can reduce its radius of curvature and its bending. I make that rope very heavy. It's going to be more difficult to flatten it out. It's also going to have more curvature. So as I increase the weight, the fallout is generally you're going to have increase in the bending stresses. As we noted from our bending stress calculation, as I increase the pipe size, I'm going to have increased bending stresses for conditions that are the same, say 1,000-foot bending curvature, etc. Conversely, if I increase tension, I get the opposite effect. I get a decrease in stresses. Now, looking at this, your project parameters or project requirements are going to dictate your pipe size. The location of your project is going to dictate the water depth. But you do have some control over how much the pipe weighs submerged in the water and how much tension you can apply to the pipe during the construction operations. So to control bending stress during the pipe lay operations, the two key variables you look at are weight, submerged weight, and the applied tension. Of course, tension being very much a parameter that's geared towards your lay barge itself. Okay. That ends my presentation. I'm going to turn it back over to Haley, and we'll be glad to answer some questions at this point.
David, thank you for sharing your expertise with us today. Now let's move right into the question and answer session, as we have several questions that were submitted by our audience members. Sarah from Alaska asks, is the point of inflection necessarily midpoint between the surface and the seafloor?
Sarah, the short answer is no, but let's go back to a slide that may help illustrate why it's not. As you get deeper and deeper water depth, more of your pipe span from the point of inflection down to the seabed is going to grow longer and longer. You find that the upper portion, or overbend, is less sensitive, or less sensitive is a good way to put it, to increases in water depth. So if you establish the tension and the basic geometry over the truss here, you'll find that there's relatively small changes in the depth that you find the point of inflection compared with the water depth. Now, the other side of that is true. As I get greater and greater water depth, this sag bend, this elevation here at the point of inflection due to the sag bend is going to change fairly dramatically. Now, another thing that does happen as I get deeper and deeper water depth is this point of inflection, the angle increases, and therefore its depth increases very slightly. But again, it's relatively insensitive for the overbend and very sensitive for the sag bend. Kind of as a point of reference, the typical range of point of inflection for the S-lay configuration and water depths in the 12 to 1500 foot range, or in the range of S-lays, is going to be in the 20 to 45 degree range. If you get into very shallow water, these numbers will even approach angles as low as 6 to 10 degrees. as you get in deeper and deeper water, these angles increase. Okay, so about 45 degrees would be the maximum angle. But in answer to your question, no, it's not at the midpoint, and it is somewhat dependent on water depth, but it tends to have relatively small amount of change for the overbend portion there of the pipeline. Okay, Haley, next question.
Claude from Germany wants to know if you can provide any guidance in maximum stress during installation.
The maximum stress limitations are usually, in fact, virtually always, dictated by company practice and company specifications. As a point of reference, the typical stress limits that you would see, and again, I'm going to use this same diagram here, in both the overbend, where we control the radius, and in the sag bend, which is a function of the submerged weight and the tension and the size of the pipe, are usually limited to about 80% of the specified minimum mule strength in the combined stresses, which would be both tension plus bending stresses. There is some guidance in some of the industry documents, like from Donarski Veritas. But all in all, this is a company decision, and most companies end about in the 80%, maybe as high as 85% in the overbend, and 75% to 80% of the specified minimum mule strength in the sag bend. Those are very, very common numbers, and I've seen them used repeatedly for the last 4 decades.
Christopher from Dave, do similar rules for maximum bending apply for radius of curvature and onshore?
Christopher, that's an interesting question, and it's if you were ever on a onshore pipeline construction job and looked down the along the ditch line during the lowering in operation, you would see that the pipe takes on a very similar flat S configuration, just as we describe here for the offshore pipelay. The biggest difference is the vertical offset that you go through. For an offshore pipelay operation, it's maybe hundreds of feet in terms of depth, maybe even thousands of feet in some of the real deep pipelay, whereas for an onshore configuration, you'd be a few tens of feet at most, and a quite common number would be a total vertical drop of the pipe from where it's been welded to where it rests in the bottom of the trench, about 10 to 12 feet. So that difference in elevation change is very important in terms of how much curvature is required to get the pipe off of the supports there alongside the ditch onshore and into the bottom of the trench. And as a result, the radius of curvatures are very, very, very large. And because they're very large radiuses of curvature, the bending stresses are very, very small. It's very rare on an onshore pipeline construction that you would have any issues in terms of the bending stresses related to the lowering end of the pipe into the trench.
All right, Lacey from Denver wants to know if you could briefly explain the major differences between S-lay and J-lay and where one would apply over the other.
Well, Lacey, as you can see from the picture I've got here, I'm showing the S-lay, but the S-lay is configuration can be a good place to start describing the J-lay. Now, for example, if we consider from the point of inflection down into the sag bend, that takes, if you kind of have a bit of imagination, that has a bit of a J shape. As I get deeper and deeper water, as I mentioned earlier, the angle here at the point of inflection will get steeper and steeper, rising through 20 to 30 to 40, 45 degrees for most S-lay configurations. And as I go to the J-lay configuration, that increase in angle continues until you can reach angles well into the 60 to 70 degree configuration. Now, at the top, rather than bending over in an overbend, you will continue and actually assemble the pipe in a near vertical condition. Imagine, if you will, the lay barge up high and the stinger being, or the assembly area and its stinger being at about a 60 to 70 degree angle. So the pipe is assembled in the vertical for a J-lay as opposed to the horizontal for an S-lay. The pipe does not have an overbend. It just comes sag bend only with increasingly steep angles until you get into the 60 to 70 degree angle configuration. And the stresses will be controlled again by a combination of the weight of the pipe submerged in the water and tension. It makes no difference whether you're talking about the sag bend portion for a J-lay or the sag bend portion for a S-lay.
Philip from Australia asks, David, how does the lay barge apply the tension to the pipeline?
All right. Well, Philip, I'm going to continue to use the same sketch here. This is a multi-purpose, multi-function sketch. First thing to think about when you talk about the tension that's going to be applied to the pipe is that I have to hold the barge in position to react against those tensions that are applied. In essence, hold the barge steady. If I don't, then it's going to move through the water. Most vessels, like the one we showed in the earlier photograph of the big semi-submersible, use anchor lines, or in some cases the dynamic position vessels. They will use big thrusters in order to hold the vessel in place and react against the tension that's going to be applied to the pipe. All right. Now let's talk about the other end, down here at the sag bend where it touches down. To react against that tension is applied and keep the pipe from sliding along the sea floor, I either have to have a sufficient pipe laying on the bottom that the soil friction will be higher than the applied tension, or, and maybe in combination with the soil friction, I'll have large anchors or anchor piles that will act to react against the tension as well. All right, so that's how I reacted. I have the vessel here being held in place by either mooring lines or thrusters, and I have the soil friction or anchors holding the pipe in place at the bottom. Now up here at the pipe on the lay barge, to apply the tension, it takes a large piece of mechanical equipment. And the versions that you typically see in today's operations look much like the Caterpillar tracks, two Caterpillar tracks, one above the pipe, one below the pipe. These tracks have large rubber pads on them that are grip and hold on to the coated pipeline itself. And they will slowly rotate and pull tension in the pipe until they get the desired tension levels throughout the pipe, and that means you've now got the desired configuration of the pipe over the S-bend and through the overbend and down into the sag bend portion of it. Now these machines are quite large. It's not unusual for a large tensioner to have 4 500 horsepower hydraulic motors to drive these elements. There's issues with the slippage of the shoes on the coated pipe, etc. So there's a lot of additional mechanical and operational issues that go along with applying this tension to the pipe. Also, the tensions usually applied to the pipe after several of the welding stations have completed their work. You have to get at least a certain amount of the welding completed before you have adequate metal area in there to take the tension and the related axial stresses that are going to be placed in the pipe to apply the tension.
Thank you again, David. That now concludes the question and answer section and our webinar. Unfortunately, we did not have enough time to get to everybody's questions and would like to apologize for that. Do feel free to send additional questions to webinar@jmcampbell.com. Thanks again for joining us, and we do value your opinion. If you have any ideas about future webinars or any comments, please let me know at the number on the screen or at webinar@jmcampbell.com. We look forward to seeing you in a future John M. Campbell & Company course. Thanks so much and have a good day.